So what I will be talking about is a programmable wireless world with reconfigurable intelligent surfaces. So my talk will be structured into three main parts. First, I will give you an introduction about what are these things that I have in the title: reconfigurable intelligent surface. What do I mean with a programmable wireless world? And then I will develop a system model for this, because this is a signal processing talk series. So that's why I think it's interesting to have at least some signal processing aspects to this, because a lot of people are concentrating on the electromagnetic aspects, but are not talking so much about the signal processing aspects. And then I will, towards the end of the talk, mention some misconceptions that are floating around in this very fast-moving topic area, and some of the key open questions that I think is very important for people to work on in the near future. So if I'm starting with the introduction, yes, so let's just talk about the basics of the physics of wireless signal propagation. So wireless communication is really about sending electromagnetic waves that are carrying information. And as any type of electromagnetic wave, they are traveling at the speed of light, and they are spreading out from the transmit antenna in all directions. So if you have the transmit antenna here, they are spreading out. You can view it as having a surface or a balloon that is blowing up, and it becomes larger and larger and larger. And the signal energy is lying on the surface area of the sphere. And if you have a so-called isotropic antenna that is radiating it equally much in all directions, well, then the signal energy is spread over this surface area equally. And if you are then putting a receive antenna at distance d away, and it have an area a, which is perfectly on the surface of a sphere of radius d, well, then it will capture a certain amount of the transmitted signal energy. So if it has area A, and you see that, okay, the surface area of a sphere with radius d is 4 pi d squared. Well, then it's the ratio between these two ones that is telling you how much of the transmitted power that you are getting as received power. So this is one way of phrasing the famous Friis propagation formula from an old paper from 1946 by Friis. This part here is what we can call the channel gain. Sometimes people are calling it the path loss or channel attenuation or something like that. And the important thing is that this is always smaller than 1, because you can never receive more power than you transmitted. We are not creating anything along the way. But what is very important to understand is that usually it's a very small number. So a typical antenna is sub-wavelength sized. So say that we are working at the 3 gigahertz frequency, then the wavelength is 0.1 meter or 10 centimeters. Then the area of the antenna might be this wavelength lambda divided by 4 times lambda divided by 4. So it's a square sized thing. In that case, if you are putting your receive antenna 1 meter away, which is very short distance, then what you will receive is still only 0.005%. So it's minus 43 decibel if you compute this ratio here and turn it into decibel scale. And if you move to 10 meters, well, then you are losing yet another 20 decibels because of the square here. So you're receiving 0.00005%, minus 63 decibels. So it's essentially like saying that if you are sending out 2 million pieces of energy, then only 1 of them will be received. And this is very important to understand when it comes to what I will be talking about today, because it's only a tiny fraction of the transmit power that is received. And that means that small, seemingly unimportant changes in the wireless propagation might make a big difference. It might lead to you doubling or even more the received signal power. So actually, in reality, we seldom have this situation where you are seeing the transmitter. You might have this situation here. I'm standing in my virtual office. There is a base station on the neighboring building. I've removed the ceiling of this building, but you can see that there is no way that this signal that is sent out from this base station can reach me and my iPad directly, but it will have to go through the wall. And in addition to those things I described in the previous slide, that you might only have 1 out of 1 million parts that you receive, well, then you will lose maybe 20 decibel or more when you're actually penetrating the wall. And what happens with the rest of the signal energy that you're sending out? Well, it's spreading out in all directions, and some of them will make it into this room as well. For example, somebody might go through this window, and windows typically have smaller losses than a wall. So the problem is that you can't see me through this window here. The signals will go in through the window and then it will reach the wall here. And then there is all kinds of wireless phenomena that are appearing. If you have a very smooth surface and you have a wave coming in, then it will be bouncing off it, and you will get some kind of specular reflection-like things where you have a wave that goes in and the shape of the wave is not changed and it goes out again. We have the phenomena of scattering, where the surface is rough compared to the wavelength. And in that case, when the signal goes in, it doesn't go out in the same angle. It sort of gets split up and sent out in different directions. And then you have the phenomenon of diffraction, where the signal is hitting a corner and then it makes it around the corner, so it's sort of bending off. And this is the type of phenomena in wave or ray optics that you are usually seeing if you're studying a physics class on optics. But optics is usually about visible light. That is what people have in mind when they're writing textbooks. And then the wavelength in optical range is typically 100,000 times shorter than what it is in the radio spectrum that we are considering, which means that if something should be considered rough or smooth depends on roughness that is at a different scale. So that means that in most cases, it is the type of scattering behaviors that you will see and potentially diffraction. We shouldn't expect the reflection to happen in this very nice way. So whenever I say reflection in this talk, I mean it in a diffuse way. The outgoing signal is a beam in a particular direction, but signals are also going in other directions. But I will come back to this phenomena in a moment. But what is then the idea of this programmable world, and what does it do with this wave propagation? Well, there is this concept of smart cities that people are more and more engaged in, where the idea is that you would try to connect as much of information in a society as possible. So say that you have a lot of different sensors and assets and resources, services in a city like Hong Kong here, and you would like to manage them as efficiently as possible. Then there's a lot of data that can be collected by different sensors. And if you can fuse them together, maybe you can make better decisions on how to use things. So you can put up a lot of devices here, Internet of Things devices. It could, of course, be mobile phones or base stations that you put on the rooftops here or that the users are using. But it could also be various type of sensors, temperature sensors, or whatever type of sensor that you can put in a factory or other places. And what you can monitor in a city is things like the traffic, the transportation systems like trains, different types of public utilities and services, things like the water supplies, for example, or the power grid. There's a lot of work on how to optimize those things as efficiently as possible. And people have hoped that you can sort of prevent crime by having a more intelligent city that could report when things are happening out of the ordinary. And the whole smart city concept is based on that you are collecting this big data, and then you should manage your assets, resources, services more efficiently. And how do you do that? Well, somehow you need to process these input signals, the data, and you could potentially use machine learning methods to sort of trying to figure out how to do this more efficiently. Can we, in addition to these type of things, also somehow control the wireless propagation in this city? Can we use the smart city concept and expand it not only to provide you with access to this data, but also sort of tweak the propagation environment so everyone can get good coverage everywhere? And what does that really mean? Well, if we look back at this example that I was describing, where I'm standing in my virtual office and you have this base station on a neighboring building, and we know that the signal is going to come in through this window here, because this base station is at a fixed location. But people can be in any place in this room here. What can you do? Well, we could put up a special surface inside of this window. This is what we call a reconfigurable intelligent surface. And we can sort of control it, and I will come back in a moment how to do that, so that every piece of signal energy that is captured by the surface is going to be instantly retransmitted or scattered or reflected, whatever you want to call it, towards me as a user. So this is showing some kind of beam pattern. The name Reconfigurable Intelligent Surface contains 3 words. Reconfigurable means that somehow the properties of this surface here, which is a very thin surface that you put on the wall, can be changed. Intelligent means that it's real-time programmable or controllable. And surface, of course, means it's a 2-dimensional array. And what it will contain is small elements that we call scatterers. And I will go into more details on that here. So this is an idea of how a reconfigurable intelligent surface could work. You have a transmitter somewhere. You have this surface. You have a user. And then you are programming the surface and control it so that when the signal is coming in here, and we know that this signal is meant for user 1, then all the signal energy that is received at this surface is going to be immediately beamformed towards user 1. And then in the next millisecond, well, now you have another user, user 2, that's interested in the signal. So let's now change it. Let the programmable controller change the behavior of the surface so that now it's instead beamforming the signal towards user 2. And how can you build something like that? Well, the basic component is that inside of this big surface, you have small elements. Each of them is a small patch. It could be something that would be existing in an antenna. It's just that it's not connected to a conventional transmitter receiver chain that allows you to generate signals or extracting the signals in the uplink. Instead, it's just something passive, but it's reconfigurable in the sense that it's somehow connected to a switch that can help you to change its properties. It could be a diode, a varactor diode, for example, and that one is then connected to this programmable controller. And it's not injecting signals to this passive patch, but it is changing its properties, either by having some discrete values that you can select, okay, it should behave in this or that way, or it could be that you are having a voltage that you are varying continuously, and that will then create some kind of continuous change in its behavior under certain constraints of what you actually can do. What is the material that you will use to build a surface like this? Well, I would say this reconfigurable intelligent surface, that is a communication concept. And then how you actually build it, it can be implemented in different ways. A lot of people are talking about something called meta surfaces or meta materials, which is some kind of strange materials that behaves in a way that is physically accurate, but you don't see this type of surface in reality. So it can reflect signals in different ways, for example. There is also a concept of reflect arrays in the electromagnetic literature. People have been working on that for 50 years. And it could also be built on various kind of conventional patch antennas. So you can find experimental works with all of these type of materials where you try to build something like this. And I think building the surface by itself, it's not a challenge for someone who is working in this field. We know how to build it in principle. The challenge is rather this reconfigurability. And in particular, to do this in real time so you can switch between these users. And there are different means of implementing it. And I will just mention those here. One would be to try to tune the impedance of these different elements. Another way that I find more easily to understand from a signal processing perspective is to tune some kind of length of delay lines. So you can think about that the signal is coming into the element, then it has to sort of propagate along a delay line and then back again, and then it gets reflected. And by tuning the length of it, you can tune a delay, for example. And there is also the conventional type of phase shifters that people are talking about in millimeter wave communications that you could potentially use as well. And what I will be talking about today is not a particular implementation of this concept, but rather if you can build something like this and you can reconfigure it as you like, what could you achieve with something like this? And what's important to understand is that a single element here makes little difference, because the only thing you can do with a single element is that you receive some piece of the signal energy, maybe only 1 out of a million parts, and then it will send it out potentially with a different delay and with a you can change things like such as a signal polarization, but not more than that. It's the joint effect of many of these elements that are needed in order to form beams in different directions. And that will become clear when we are setting up the system model for this. So what is the idea then with the programmable wireless world? Well, the idea is that this RIS, the Reconfigurable Intelligent Surface, as a whole should be able to control various things, such as that when a signal comes in, what will be the directivity of the scattered signal? It will form a beam in a particular direction. And you can potentially also decide on that, well, I don't want to scatter anything. I would like the energy to just come in there and then it's absorbed. Or potentially you will change the polarization. And here's some example of things you could potentially do. So here is our library at Linköping University. And we know that if you're working in millimeter wave communication, for example, the signals are not propagating very well through different materials. And you might have users at these different floors here. So what if you put up a base station at the top? And then in order to make sure that the signal gets spread into the different floors, you could put up these type of surfaces at different places. And then the signal that comes from above hits the surface, and then this beam formed into this part of the floor, or this part is reflecting over here, and then it continues like that. So in this way, you can improve indoor coverage, and you can make sure that the signals are getting a good reflection, and you are getting line of sight like properties. The signal doesn't have to rely on penetrating different materials. Here's a meeting place in Lucca where we'll have the sport conference next year. And suppose that something hidden is going on here. We're talking about something that people should not be able to eavesdrop. And if we are using wireless devices here in one way or the other, then the signals might be able to propagate through the walls here. And we can cover the walls with this type of reconfigurable intelligent surfaces and configure them so they are absorbing everything. Instead of just scattering it, they're absorbing it. In that way, nothing will propagate through the walls, while otherwise it will just be the passive materials that is determining how much that is penetrating the walls. And if you look at more outdoor scenarios, here I'm standing in a hotel room in Melbourne, and you have a lot of different places, you have a lot of different buildings, and big buildings can shadow other buildings, and you don't want to put up base stations everywhere. Unless I can see a base station here, I won't get a good signal. But what if you, on some of the building facades, are putting up this type of reconfigurable intelligent surfaces, and then you are figuring out, okay, now this guy in this hotel room here would like to get a good signal. Well, then we are configuring these surfaces to reflect the signal towards me as a user. So these are some of the ideas about how you can program the wireless propagation both in the local areas and in the larger areas in order to get a better wireless world. And even if you just can contribute with a little bit of signal power, we know that a little bit of signal power can make all the difference, because you are usually only getting 1 or a million or 1 billion part of the signal energy receiving. And you can argue that, well, why are you trying to talk about these alternative methods? Or why are you trying to create something new, reconfigurable intelligent surfaces? Why don't you do any of the classical approaches, such as deploying more base stations? Well, we already have a very dense deployment of conventional base stations, and every time you put up a base station, you will have to have all the infrastructure for power delivery and backhaul. Typically, a base station might need a kilowatt of power or more, and you will need a high-speed backhaul. You maybe don't want to put that everywhere. So that's why this reconfigurable surface could be useful. And they're also creating more and more interference. So you will have to coordinate their decisions more and more if you have a lot of base stations in order for it to work out well. And you can also talk about, well, we have the relaying technology, half duplex relays that you put up on different places. You send the signal from one place, it's received here, and then when you have received it, you repeat it to another place. Relays are, for example, used in tunnels to improve the coverage. And that is sort of the same concept here. You're sending a signal, and then you have a reconfigurable intelligent surface that is reflecting it here. And the difference is that these reconfigurable surfaces are semi-passive. You are reconfiguring them, but they're not adding any signal energy to the propagation. So in that way, they could potentially be much less energy hungry. And you also you can put it in a more transparent way into the system, because you don't need to let the base station turn on and off its transmissions depending on when it's time for the relay to transmit or not. If you are putting up these type of surfaces, they are working in what we call full duplex operation. They are just there. They are passively reflecting, and they are sort of adding additional paths to your propagation environment without having to have a dedicated time for doing that. And you can also say, well, why don't we just skip this concept and we are using better materials that are not blocking our wireless signals, so that the millimeter wave signals are going through the walls, or when we're moving up even further in the frequency domain, we would like the signal to just propagate through the walls much better. Well, the main reason for putting up walls in your buildings is not to have good wireless coverage, but to have a good thermal insulation, so that in particular in Sweden, when it's cold in the winter, we will like to be making sure that we can keep the heat inside, and that also keeps the signals outside. So it's hard to achieve thermal insulation and also get signals through. And even if we put up passive materials like a metal sheet on the building so that the signals are getting reflected in a good way, it's not sure that the signal will happen to just hit in the direction where you happen to be. Usually, if you are studying wave propagation, you know there's Snell's law that says that if a signal goes in with one angle, it will go out with the same angle. That is not at all guaranteed to hit you where you are as a user. So the main use case of these surfaces would be to focus signals at the user. So it's sort of a way of expanding the size of your antenna in the receiver, because if you have a mobile phone with just a small antenna inside of it, you cannot capture more energy than you have inside of that surface area. But if you are thinking more like a satellite receiver, where you have this type of dish antenna that is capturing a lot of energy and that is focusing at the receiver, you can view these surfaces as a way of synthesizing the same idea. So say that you have an incoming signal. I'm showing it here. It's a plane wave that comes from the left, and then it hits a curved metal surface here. And this surface is curved such that the signals are going to be focused at the receiver at a particular location. And that means that all of the energy that is hitting the surface here will ideally appear at the receiver here. And this is just a passive surface. So the place where the signal will be focused, where you would like the receiver to be, happen to be the place where all of these paths here are equally long. And the way that I've described it here is like, okay, the signals is consisting of rays. Here you have one ray, here you have another ray, a third, a fourth, and fifth one. And then it goes like this. But radio waves are generally not described by rays. It's never consisting of rays, but it's a good approximation in optical range to say that we can break down the wave into rays, and then you can compute how each of these rays here are being reflected. But in general, the way to view how this works is that when one piece of the signal is hitting the surface, it will be scattered in all directions from the surface. This is something called the Huygens-Fresnel principle. And you can view it as at every point on the surface here, you will have like a point source that is scattering the signals uniformly in all directions. And then, depending on the phase shifts or the time delays of these signals, these waves that are propagating from these different places on the surface, at some places, they will be received in phase. They will have exactly the same time delay, namely where the distance to this receiver is the same. And at those places, you will get a strong signal, and other places you won't. So here you will get a beamforming because all the paths becomes equally long and also the delays are the same. And this is what we are trying to synthesize with a reconfigurable intelligent surface. And it's not a curved surface, it's supposed to be a flat surface. But in the surface, we have these small elements, and when one piece of the signal is hitting this element, it's also going to be scattering the signal in all directions. But what we can do is that we can process the signal. We can filter it inside of the surface here so that we can make sure that still at the same location here at the receiver, we will getting the strong focusing. And what you can view this is that you have a incoming signal here, S of t, and you have n different elements. And for each of these signal pieces here, you will get a signal, S of t. It will have a propagation delay, which you can compute by taking the total length here. And then you have an additional delay within the surface. I call it delta n here. So in each of these elements here, you can add a delay, and that is a controllable thing here. And then what you receive here is a summation over the signals, and then you have a channel gain here that says how much you have lost along the way, but that's not the important thing here. The important thing is that you would like all of these pieces here in the sum to be adding in phase. So you will have the same delay here. So that is what you are doing in order to synthesize this type of shape here. You make sure that tau n plus delta n is equal for all the n at a particular location where you would like the signal to be focused. And since what you can control is time delays here, and a delay must be a positive amount of time, well then the sort of causal solution to something like this is to make sure that they are equal, and they are equal to the largest of these different delays. You take the element here that is furthest away, that one adds no delay at all, or the minimum delay you can put there, and then the other ones are delaying it, their things in such a way that you are synthesizing a surface that is focusing the signal at the receiver. Okay, so how large would these different elements in the surface be? Ideally, we would like to be able to continuously change the delays. So this color here is showing what are the delays. So if the signal comes in from a particular direction, you would like to go off in a different direction. You can compute what kind of delays you would like to have, and you would like to be able to continuously change them in the surface. But of course, in reality, it's very hard to change something continuously. So you would instead discretize it. So you have different elements at a particular size, and each one of them will be scattering the signal with a particular delay that we can control. And if you zoom in at one of these elements, and you say that the signal is coming in from minus 30 degrees here, then we know from what we call Snell's law that if you have a passive surface, the signal will go out with the same angle from the orthogonal direction here. So we will be strongest in the plus 30 degree angle direction. And if we look at surfaces of different sizes, if it's half the wavelength and half the wavelength, you get this red curve here. And this is a normalized gain, how much signal is radiated in a particular direction. And we can see that most of the signal energy is going out in that direction, and much less in other directions. If you make it smaller, lambda by 4 times lambda by 4, you get the blue curve here. Now you still have the strongest direction according to Snell's law, but the variations are smaller. And if you make it lambda divided by 8 times lambda divided by 8, you have a much more flat description here. And what we would like to be able to control is the direction. You don't want a particular element to have a preferred directivity determined by where the signal happened to come from. You would like to be able to tune this perfectly depending on where the user is. So you would like to have a small element size. So you get this black one here, and then you can tune the phase delays so that you can form beams in different directions. So each element should scatter the signal almost uniformly. So you would like to be down at like lambda divided by 8 or lambda divided by 4. These type of cases is the sizes of the elements that people are considering. And I'm talking today about reconfigurable intelligent surfaces, but there's a lot of different names for the same idea. People have been talking about intelligent walls or software controlled metasurfaces or reconfigurable intelligent surfaces or reconfigurable AI metasurfaces or intelligent reflecting surfaces. And in my overview paper from last year, we were mentioning all of these ones. And maybe some people are reading slightly different things into these different terminologies, but I think in a general sense, they mean the same thing. So you can just pick one of them, and I think there is some kind of convergence towards that people are calling it reconfigurable intelligent surfaces. Okay, so since this is a signal processing topic, let's go in a bit more and talk about the signal processing aspects and develop a signals and system description. So you have a transmitter that sends a signal to this element. You have a receiver over here, and let's look at just the channel to this one of the elements. So you have a channel here, you have a channel here. And the way of describing this with signals and systems would be that you're sending a continuous time signal. The channel is a filter with an impulse response. The element here is a reconfigurable filter. So it has an impulse response, also depending on which element it is here. And then you have a control variable theta n that you can somehow control, decide on how the filter should behave under certain circumstances. And then you have a channel to the receiver. It's also described by an impulse response, hn of t, and you have gn of t. These two are given by nature, and this is what we can sort of reconfigure. And then we know from signals and systems that the received signal y of t is going to be a convolution between the different impulse response of the filters here and the transmitted signal. So this is what we are going to be receiving. And let's focus for simplicity on a narrow band system where the signal that we're sending is just a complex exponential. E to the power of j, the imaginary number, 2 pi. We have fc, which is the carrier frequency in the complex baseband, and then we have a t, which is time. And the filter, let's just call it, it has the impulse response g of t, or frequency response to Fourier transform g of f. Then the received signal y of t is going to be a convolution between g of t and x of t. And if you write it up, it's going to be this integral here. From minus infinity to infinity, we have the impulse response here. Then you have x of t. You replace t by t minus tau. And then you are integrating here. And what you can observe is that we have one term here, e j 2 pi fct. That is, doesn't depend on this tau here. You put it in front. And then the rest of it is actually the definition of the frequency response, the Fourier transform of this. So we can write the output as the frequency response for a particular frequency, the one that we're using, and then we have just the original signal here. So this is how these type of systems work. So what happens is that the transmitted signal, when it only have one frequency, the amplitude is changed based on the frequency response amplitude, and then you have a phase shift or a time delay as well, also determined by the filter. And what that means for us when we have a received signal, which is the convolution between two channels and the filter in the element, is that we will just get the received signal, which is the product of the amplitude changes that you are getting from the two channels and from the element. And then we have the transmitted signal when you have this x of t, and you get a joint phase shift or delay that is determined by the argument of the two channels and of the element. So let's make it simple and consider a case where we have a line of sight channel from the transmitter to the element here and from this element to the receiver. The distance is dn, and here is delta n, and the area of this element is a. And then remember the first technical slide I had where I was saying that this Fourier propagation law is saying that the path loss or channel gain from over a line of sight channel is the area of the receiver, a, divided by 4 pi, and then you take the distance, which is dn square here. And then since we are talking about things in the amplitude domain here, we take the square root. And then you get a propagation delay, which is determined by, here you have from the signal, and then you can say that the signal needs to propagate dn distance, and it propagates at the speed of light. So this is delay. And in the same way, the line of sight channel that you have from the element to the receiver have the same shape. You still have an area A here, you still have the delta n square here, and then you have delta n here, which in the delays. And the reconfigurable filter, that is the one where we can control somehow. It has also an amplitude change, and it has a delay here. And to make it simple, let's call this phase shift on the first channel phi n, and here we have var phi n, it's the same phi both cases. That means that when we are computing our received signal, it should be the product of these different frequency responses and the signal that we're sending. In that case, you get the product of these amplitude parts. You have this here. So you have the area, you have 4 pi, you have the product of the two distances. Then you have the amplitude change from the reconfigurable filter. And then you have the joint effect of this phase shift, and this phase shift. And what we can tune is this amplitude that you get in the reconfigurable filter, and it's something between 0 and 1, because we can decide on if you put 0, we are absorbing everything. If you put 1, we are scattering everything. And then we can change the phase here. Let's say we can change from 0 to 2 pi. In some cases, you can have a larger range. It doesn't really matter from a signal system point of view, but it determines the actual delay that you can create. And that was then the signals and system model for just one element. But if we are having a large surface here with a lot of elements, capital N elements, and you would like to focus the signal at this receiver here, then the received signal here will be that you take the transmitted signal, you multiply it with what I was computing on the previous slide, this joint effect of the channels and the surface for one element. You sum it up for all elements, and then you add noise, and that way you get the received signal. And the signal processing problem will then be to maximize the signal to noise ratio. And by doing so, you will be actually forming a beam towards this user, or focusing the signal at the user. And it is then the summation here that you would like to make as large as possible in absolute value square. So if you look at this channel gain here, you take this term here and you take the absolute value square of it. You would like it to be as large as possible. Well, one way of viewing it is that, okay, you're summing up a number of terms. And if you like the sum to be as large as possible, you will like all of them to be positive, or at least have the same angle in the complex domain. And in that way, you will add them up, and then you will also like them to be as large as possible. So that would mean to make sure that this phase term here is the same for all of the n elements, and that you select this mu n to be as large as possible. And you can also show this mathematically using the Cauchy-Schwarz inequality, that you would like to make all these phases the same. So you get something like this, and then you take mu n to be equal to 1. So you achieve this when all of these different summations are the same. And as a final step, we can also say, okay, usually when the user is far away, it's important to remember that the phases are changing, but the path loss is almost the same from all of the elements. So if you say that these dn and delta n are approximately the same, well, then you will get something like this, where you can take away this subscript, and you are just getting n squared, because you have a summation and you have a square. So you get the square of number of elements, and then you get this path loss term for each element. And to show you some basic performance benefits of using this type of surfaces, say that we have a transmitter transmitting to receiver, and you have put up a intelligent surface here. And you have -75 dB here, -75 dB here on these channels. And then between transmitter and receiver, we have two cases. One when we have a bad channel, and one when we have an equally good channel here. And we have some reference transmit power here. In case one, when you have a relatively bad channel between transmitter and receiver, the spectral efficiency in bits per second per hertz that you can achieve as you're changing the number of elements in the surface here is varying like this. If you don't have any RS at all, you get this baseline curve, it's a constant. While when you are having a surface, you get a red curve, and you see that it's increasing rather rapidly with the number of elements. So then it pays off a lot to have a surface, even if it's relatively small. You can double your spectral efficiency or more. In the case when you have a relatively good channel from the beginning, you already have a quite high spectral efficiency. You still gain from adding a reconfigurable surface, but you will need to have a much larger surface before you are seeing the good gains here. So I would say that these surfaces are particularly useful when the direct path between transmitter and receiver is blocked somehow, so that it's relatively weak, and then you can add an additional path that, even if it's relatively weak, it's still good enough to get you a good performance gain. So I will wrap up by briefly mentioning some of the misconceptions and open problems in this field. So I have a paper called Reconfigurable Intelligent Surfaces, 3 myths and 2 critical questions, and I won't dive into them in any detail, but just to read them up for you. The first myth that some people have been spreading in literature, because this is a very fast changing literature. People like to say that current technology cannot control the propagation environment at all, and now we have this reconfigurable surface that can do that. But the truth is that a reconfigurable surface is a relay that is getting a signal there and then scattering it. It's not a regular type of relay that usually is amplifying the signals before retransmission, but it still is a type of relay. And relays have been existing in standards since 3G. So it's not a new feature per se, but it is a type of relay with very unique properties that might make it much more useful than previous technologies. So that's why it's still very interesting to look into. Another myth is that these intelligent reflecting surfaces or reconfigurable intelligent surfaces have a better asymptotic array gain or improvement. You saw that the SNR that I was developing scale with the square of the number of elements n. And if you are just considering regular beamforming from an array with n elements of the same size, then you will only see an SNR that grows with n. And that has led some people to believe that, well, n squared is of course better than n, right? Yes, asymptotically, you know that this a curve that is increasing faster would always cross another term. But the problem is that this description here was based on that I said that the dn and delta n was the same for all of the elements, and that only holds when you are in the far field. So if you would be comparing here the SNR, depending on the surface area, with this reconfigurable intelligent surface, and with some kind of other classical things like a half duplex relay, that relay is getting a much higher SNR. It doesn't grow as fast with the surface area of the array. You see the faster scaling here due to this n square, but when you would expect the intelligent surface to cross it, well, then is when we are leaving the far field. In that case, you won't see this type of behaviors anymore. So it's not like you should trust the scaling behaviors and say that one technology is better than the other. It's instead that you should compare a, say, 1 meter times 1 meter passive reconfigurable surface with a more active single antenna decode and forward or other half duplex relays. And in those cases, a larger surface can be traded towards having a lower energy consumption. That is sort of the idea. And another misconception is that you should view these surfaces as being a plane mirror. And a plane mirror behaves like this. If you have a transmitter that sends a plane wave here and it bounces off an infinitely sized mirror, then you will see a plane wave go through here. And then, as you can see, the receiver is only capturing a small part of it. And if you are looking yourself in the bathroom mirror, you only see yourself in part of the mirror. The rest of it is wasted. But that is not the case with the reconfigurable intelligent surface, because even if you have a finite sized surface here, what you are doing is that you're synthesizing this type of curved surface so that you are focusing the signal at the receiver and the entire surface is useful. So we can greatly outperform a plane mirror. So we shouldn't think about this as some kind of special mirrors with what you call anomalous, which means that you can change the reflection angle. It's something completely different that you can be much better than that. So what are then finally the open questions? Well, one thing is that we still lack a really convincing use case for these type of things. I've been describing that, okay, we would like to create this programmable world, which is sort of a fluffy way of describing that we would like to make something better. But what we should remember that in the work for 5G communications, some methods that people were investing a lot of research time into took off. Massive MIMO, which I've been working on, is now used to increase the spectral efficiency in 5G. And the millimeter wave technology is used to be able to have more bandwidth. And the combination of these two things is also very useful. But there's also other things that people are branding as, oh, we're going to have this 5G topic here. There is what is called NOMA, non-orthogonal multiple access, and there is something called spatial modulation. Both of them have been sold in the literature as being 5G topics, and none of them are in 5G right now. And it's also not clear if they will be included or not. And that doesn't mean that they are bad technology per se. It just means that the way that we were trying to develop them was not based on showing the right gains towards the right baselines. So what we need to figure out is, what are reconfigurable intelligent surfaces really good at? Something that can be improved by 10 times, some kind of metric, spectral efficiency or something else, over competing technologies. It's not enough that you can say, if you have a system without the surface and you put in the surface, it's going to be better. Yeah, but you can also put in something else and it will also be better. But what can it do that no other technology can do? And that is sort of where NOMA and spatial modulation failed, because there were alternative technologies like these ones that were much more convenient to use. And there's no good answer yet. I have some thoughts. I think that these intelligent or reconfigurable surfaces can enable operation when you have a very sparse channel, say above 100 gigahertz or already in millimeter wave bands. You have a huge amount of bandwidth, so you can achieve a huge data rate, but only if you receive a signal at all. And the signal gets easily blocked by your hand or by different elements. And you would like the signal to be received to your mobile phone from all possible directions, so that you're hopefully not blocking it from all directions as user. And it will not be so economically feasible to put up active arrays everywhere. So from that reason, you can have these kind of passive surfaces that improves propagation conditions. And as you're also moving up in frequency, you can enable much larger arrays using this type of passive approaches than you would be able to do when you have a active massive MIMO type of array. The second open question, which I will just briefly mention, is that you need to sort of learn the channel somehow. And the surface is passive. So how can you know what kind of phase delays you are going to add at different places? Well, there are some initial thoughts about how to do that. One is the codebook approach, where you have a transmitter that is sending a signal to the surface, and then the surface is changing how it's reflecting the signals, switching through different configurations while this transmitter is sending the same known signal over and over again. And then the receiver is figuring out what configuration that's preferable, tells the control about that, and then you operate like that. The problem is that you have very many different configurations. It scales with the number of elements. And if you have thousands of elements, this might not be a good type of feature. So some people are thinking about, can we use parametric models for this, estimating positions and angles, or can we use machine learning? There's a lot of thoughts about that. And there are also some thought about changing so that some of these elements are active. And while it's already known how to build a physical surface, the reconfigurability feature and the channel estimation that goes into that one, it's still unknown if we can do that in real time. So, to wrap up, is a programmable wireless world possible? It's easy to say that conventional technology can only control transmitter and receiver. We have no control over the propagation environment, and now we have a new technology that can control the entire wireless propagation. The truth is that we can control some minor parts of the wireless propagation, and that might be enough. We should also remember that an active MIME array can do anything that a reconfigurable internal surface can do. For example, the beam width is exactly the same when the arrays have the same size. So it's rather about figuring out what are the cases where it's much more convenient to have a passive surface. And the hope and vision is that reconfigurable internal surface can make a real difference for the wireless propagation, and it will be much more cost and energy efficient to use this technology compared to other ones. If you would like to contribute to this field, I think it's very important to first learn at least the basics of multiple antenna communication, because this is sort of having a multi-antenna link from transmitter to the surface and from the surface to the receiver. And I will take the opportunity to recommend my book, where you can read about these things. You can download it from smimebooks.com. It's for free. And here are some self-references that you can read. You can look at the slides afterwards. And if you would like to know some more about the channel modeling, something like that. And I think you should really try to look behind the hype. There's a lot of papers coming up every week on archiving this topic, but there is much fewer works that actually are concentrating on these two open questions that I was mentioning. And finally, I also recommend you to check out my other YouTube videos, both on this topic and on other beyond 5D and 6D topics.